Hey guys, so today we're going to talk about three separate areas of atmospheric pollution. First thing we're going to talk about is photochemical smog. We're going to move on to a phenomenon called thermal inversion that is not in and of itself a type of atmospheric pollution, but can exacerbate atmospheric pollution. And then we're going to talk about how we can reduce or eliminate pollutants at the source. So let's jump right in and start by talking about photochemical smog. So, photochemical smog. First thing is, what is smog? So you might remember that we talked a little bit about smog being a portmanteau or a combination word where we've taken smoke and fog and combined them together to get the term smog. And you have this TED Ed video that you're going to watch. So we really have two main categories of smog. We have what we call gray smog or industrial smog, and we have photochemical smog. So we're going to quickly define what industrial smog or gray smog is. This is the type of smog that's caused by sulfur dioxide and particulate matter combining with water vapor. The biggest cause of industrial smog is the combustion of coal. Remember, coal is the #1 contributor to sulfur dioxide in the atmosphere. One of the characteristics of industrial smog is that it does tend to be gray, and it really most commonly forms in cool, humid conditions. So this is the one we think of as a London fog. This was very common at during the Industrial Revolution, which is why we associate it with London. It generally forms more often in the winter. It's sometimes called a pea soup smog. So, caused by sulfur dioxide and particulates. Now, when we talk about photochemical smog, this is a brown smog, sometimes called a yellow smog. Very, very different in when and where it forms, because unlike gray smog that forms in cool, humid conditions, photochemical smog forms in dry, warm conditions. And again, big difference in the cause, because the biggest cause of photochemical smog is vehicles, specifically cars, because they emit nitrogen oxide compounds. And so photochemical smog is caused when volatile organic compounds and nitrogen oxide compounds react with oxygen or ozone in the presence of sunlight and heat. So this is a summer smog. Very, very different from the winter smog, the industrial smog. So just a quick review, volatile organic compounds are organic chemicals. That means they always contain carbon, usually carbon and hydrogen, sometimes carbon, hydrogen, oxygen, maybe some nitrogen, lots of other compounds. But in order to be organic, it has to contain carbon. And they evaporate quickly at room temperature. This is a very diverse group of compounds. Really, the unifying characteristics are that they contain carbon and that they have low boiling points, or they evaporate quickly at room temperature. There's a wide variety of volatile organic compounds. They could be natural. Plants release lots and lots of volatile organic compounds. They sometimes release them as a signaling mechanism to let other plants know that there's a problem, or to send out a scent that might bring a bug that would eradicate another bug. They use them to stabilize their membranes. They use them to build up a defense. So volatile organic compounds are a really, really important part of the plant life cycle. So anytime we have lots of plants, particularly large plants, trees and forests, then we're going to have lots of natural volatile organic compounds. We also have anthropogenic or human-caused volatile organic compounds. These might be solvents, paint, dry cleaning fluids, gasoline. These range from harmless to very, very toxic compounds. So just because something is a VOC doesn't make it a bad chemical. Almost anything that you can smell is a volatile organic compound. We talked about bakeries as one of the sources of volatile organic compounds. Bakeries smell great, and there's very little that a bakery puts off that's bad for you. However, it is putting out lots and lots of volatile organic compounds, and that's the source of all those delicious smells. So why are we talking about volatile organic compounds? Well, the combination of volatile organic compounds and nitrogen oxide compounds, those NOx compounds, they react with oxygen in the presence of heat and sunlight. And they form our secondary pollutants, ozone and what we abbreviate as PANs, which is peroxyacetyl nitrate compounds. These are oxidizing, or what we call photo-oxidizing compounds, photochemical oxidants. And that means that those are compounds that are very likely to oxidize something else, meaning that they are going to cause something else to lose electrons. And so that means that these are very reactive compounds, very active compounds. So we can have a simple graphic like this one, or we can go with a very, very complex graphic like this one. We're seeing the same thing here. We can go even simpler when we have on the right here, we have a diagram of photochemical smog. On the left, we have a diagram of industrial smog. Notice the big difference is that one happens in moist, humid air and one happens in warm, dry air. So these photochemical oxidants enhance the formation of particulate matter, which scatters light, and that's what we see as smog. So those photochemical oxidants, we come back to those, they're reactive compounds that remove electrons from other substances. That action of removing electrons from other substances is really what causes damage to the other substances. So we have the PANs. This is an abbreviation we should definitely know for the AP Environmental Science exam. That's peroxyacetyl nitrates. Ozone is also a photochemical oxidant. Aldehydes, formaldehyde, lots and lots of other photochemical oxidants out there. But the PANs and the ozone and the aldehydes are the three that you really need to know for the AP exam. So how do we remember PANs, and how do we remember that they cause damage to plants? Well, we can remember that they harm plant tissue, they cause respiratory problems because when they're scavenging electrons from us, that's not a great experience for us. Eye problems for the same reason, even cause damage to construction materials. So we can think that when we hit something with a pan, it causes damage. So that's how we remember the peroxyacetyl nitrates. Okay, so we know that this photochemical smog is caused by the reaction between volatile organic compounds and nitrogen oxides. So let's take a quick look, because these cycle through the day, and this is an important cycle that we need to know and understand. So if we look at this little graphic, this is a very old school graphic. This is from an early AP Environmental Science exam. We want to think about, when are those nitrogen oxide compounds concentrations the highest, and when are ozone concentrations the highest? Well, if we take a look at the time of day and we look at the nitrogen oxide compounds, we see that through the morning that the nitrogen oxide monoxide is increasing, and then the nitrogen dioxide increases right around 8 o'clock. So what's happening about this time? This is rush hour. So as cars hit the road, the nitrogen oxide concentrations go up. So that's why we're seeing this big spike here. When are these oxidant concentrations the highest? Well, they're higher later in the day, after noon. So we have the formation of the nitrogen oxides and hydrocarbons coming from our rush hour. We have reactions during the day in the presence of sunlight, and suddenly late in the afternoon, we have concentration of oxidants spiking. So this really has to do with human patterns that as we go through our day and we have rush hour, we're going to increase nitrous oxides and hydrocarbons. And then later on in the day, we have more ozone, more oxidants because they're produced by the reaction of these nitrous oxides and VOCs with sunlight. So what are the harmful effects of photochemical smog? Well, lots of harmful effects for humans. They are irritants, respiratory irritants, so they can irritate the throat, they can irritate the nasal passages, the sinuses, they exacerbate asthma and bronchitis. They can cause damage to the nervous system and result in pulmonary inflammation. So lots and lots of major harmful effects for humans of photochemical smog. So if it's that bad, what can we do about it? Well, the number one thing that we can do to reduce photochemical smog is to reduce its components, the things that lead to it. So what can we do specifically to reduce nitrogen oxide compounds and volatile organic compounds? So drive less. Whether that means carpooling or taking public transportation or taking riding a bicycle, walking, anything we can do to drive less is going to reduce photochemical smog. If we have to drive, take care of your car. Make sure that it is tuned up, that it is running at its best, because that's going to improve gas mileage and it's going to reduce emissions. We can fuel up during the cooler hours of the day, at night or early in the morning, because this means that the gas is farther away from its boiling point. So we're going to have fewer gas fumes heating up and joining the atmosphere and therefore producing ozone. We can avoid products that release high levels of VOCs. So when you're shopping for paint, buy low VOC paint. And then we can avoid gasoline powered yard equipment like lawnmowers. Maybe we can use an electric one, or maybe we can use a hand mower for our mowing. So we have lots of options for reducing photochemical smog, things that we can do individually. There are also things that the government can help with, as far as increasing access to public transportation or creating incentives for driving less or for using products with lower levels of volatile organic compounds. Okay, and we'll talk more about those governmental methods in just a little bit. So let's talk about the idea of a thermal inversion. So thermal inversion, first thing we want to think about is normally, what is our situation? So normally the area of the earth that is closer to the surface is warmer because the surface of the earth is warmed by the sun, and then that warmth is radiated back out. And so it's generally warmer closer to the surface, and it gets cooler as we move up through the atmosphere. Now, when we have a thermal inversion, there is a layer of warm air, and that layer of warm air traps cool air underneath it. Why is this important? Well, when we have this layer of warm air, we know the layer of warm air is less dense. And because it is less dense, as the cool air tries to rise up, it can't rise through this less dense layer because less dense is going to float on top. And so that cool air is forced to circulate back down. That means that if we already have polluted air, that pollution is being trapped by that inversion layer, by that warmer air layer. So This is very common in valleys. We can see that in this picture here. If you've ever been skiing, you'll sometimes hear them talk about thermal inversions because it's very important for ski resorts when they have these thermal inversions, that it changes the way that snow falls on the mountains. So what situations are going to lead to thermal inversions? Well, there's a lot of different circumstances that can lead to a thermal inversion. If you have a warm front with high pressure, that sometimes leads to a thermal inversion. As I said earlier, valleys definitely experience more thermal inversions. On the west coast, when we have areas of oceanic upwelling, then we sometimes have a cooling from the ocean, and then that cooling pushes the warmer air up, and we get that thermal inversion. Oceanic upwellings don't happen nearly as much on the east coast. The number one situation that leads to a thermal inversion is when radiation from the earth exceeds the radiation received from the sun. And so when does that happen? Well, it happens at nighttime and it happens in the winter time. This is very common at the poles during the winter. It's almost always present over land in the poles in the winter. Generally speaking, we only get thermal inversions on land because the ocean has such high specific heat or high heat capacity that it retains its heat. So a thermal inversion is not in and of itself a form of pollution, but when we have a thermal inversion, and we can see this image of Seattle, when we have a thermal inversion, it traps those pollutants near the earth. And so it doesn't cause pollution, but it exacerbates already existing pollution. Okay, last thing for today then is to talk about reducing air pollutants. So how can we reduce air pollutants? Well, we can use regulatory practices, we can use conservation practices, or we can use alternative fuels. So when we talk about regulatory practices, we're talking about something that the government puts in place or a local government puts in place in order to either incentivize good behavior or punish bad behavior. So an example of this is the idea of a vapor recovery nozzle. Vapor recovery systems prevent fumes from escaping into the atmosphere when you're fueling a motor vehicle. This was an EPA requirement starting in the 1990s. And it was designed to capture the vapor when you were fueling a car and returning it back to the storage tank. Since 2006, all cars manufactured in the United States have a built-in vapor recovery system. So the EPA actually phased out the requirements for these vapor recovery nozzles starting in 2013. So you can see that this is a case where a regulatory system worked and then allowed a shift away from that regulation. Another example of a regulatory practice, which became then driven by the consumer market, is catalytic converters. These started being required in the 1970s. And what a catalytic converter does is that it catalyzes a series of reactions, first reduction and then oxidation, so that it converts nitrogen monoxide into nitrogen dioxide and then into nitrogen and oxygen. It converts carbon monoxide into carbon dioxide, and it converts hydrocarbons, that's usually your uncombusted fuel, into carbon dioxide and water. So harmful gases go into the catalytic converter and less harmful gases come out of the catalytic converter. So those are on cars. Now, what about in industrial environments? So we can talk about scrubbers. We have dry scrubbers and wet scrubbers, and scrubbers are designed to remove particulates or gases from industrial exhaust streams. This is basically to clean up what comes out of a smokestack. So when we talk about a wet scrubber, you have usually a contaminated gas stream that's moved through a scrubbing liquid. It's just bubbled through. That liquid is usually nothing more complicated than water. And those particulates and gases are collected in the liquid. And so this device is used very, very often when an industry wants to collect particulate matter and gas emissions in a single system. We also have dry scrubbers where our dry reagents are sprayed into an exhaust stream. Pollutants could be neutralized if they're acidic or basic. They could react with the reagent that is sprayed into the exhaust stream and turn into a different substance. Um, that substance may be a safe substance, which can then be emitted, or it could fall out of the gas stream or be caught in a particulate screen. So dry scrubbers use a spray of dry reagents. Wet scrubbers pass the exhaust stream through some sort of a liquid. A lot of coal burning power plants use scrubbers called electrostatic precipitators. And what an electrostatic precipitator does is it gives a charge to any particles passing through. They gain a negative charge and then they're attracted to a positive plate. So this is another example of a dry scrubber system. And then one more very common process is desulfurization. This is used to reduce sulfur dioxide emissions. When coal is burned either in a fluidized bed system or near a calcium carbonate bed, the calcium carbonate reacts with the sulfate or the sulfur dioxide that is produced and produces calcium sulfate, which is also known as gypsum, which is the raw material for sheetrock. And so, although this is a relatively expensive system for industries to set up, it actually allows them to clean their exhaust and provides them with a good that they can then sell. So, solutions have to be multi-part. We have to have regulation, we have to have conservation, and we have to have some alternatives. So in the conservation practices, we want to think about energy efficient power generation, energy efficient buildings. We want to come up with better waste management. We'll talk more about that in our next unit. Greener and more compact cities, because this is going to allow us to use less fuel for transportation. Access to clean, affordable fuels is really important, and safe and affordable public transit. So when we talk about regulatory options, sometimes this might be local control measures. So this might be a city council stepping up to subsidize the switch from one type of dry cleaning solvent to another in order to reduce the levels of VOCs in the air. This could be the use of recovery nozzles at gas stations. That was a nationwide program, but the phasing out is actually run state by state. Again, some local regulations. In some areas, lighter fluid is not allowed to be used because it is a VOC and burning it produces more volatile organic compounds. There are also restrictions on wood heaters in homes. And there are, again, national regulations as well as local regulations. In some areas, you'll see odd and even driving plans in order to reduce the number of cars in a city on a particular day. So that's kind of a regulation from the punishing or restricting side. Another thing that areas can do is incentivize public transportation by making it more appealing or by making it less expensive, because public transportation reduces pollution drastically. Another one that is frequently used in local areas is HOV lanes or something similar that encourages carpooling, or using tolls to require or encourage carpooling. And so all of those are devices that are used to incentivize behaviors that reduce our emissions. So, as always, if you have any questions, let me know.